So I just share my screen. So there are two types of connection for base plate, right? So can anyone tell me uh, these two types are visible on the screen? Which one is pin type connection and which one is fixed type connection? Fixed base and pin base. You assign some support condition in STAD analysis, right? So whatever STAD assumptions we made, that we have to reflect in our drawings. For concrete, it can be easy, even if we consider some pin connection or release for the beams, but still we provide some top reinforcement. But in case of steel, it's not possible. If we have considered pin connection, then we have to detail out the connection as per our assumptions. So if these two are the connection, so which is pin connection, which is fixed connection, and why? Any idea?
Yes, sir. Fixed connection is the second one. Pinned one is the first one.
Okay, and why it is?
Because this is connected in part of web area. This bolt are coming in web area.
Okay, and for this,
Here outside flange area bolts are given.
okay, right. So when we provide bolt inside the flange, then the this connection is not able to take any movement because of very small lever arm between the bolts. But when we provide the bolt outside the flange area, then we will get this much of lever arm between the center of bolts, center to center bolt. This much distance we get as a lever arm, so that the total movement, whatever movement is there in this plane, it will get converted into pull push or tension and compression. So one side will be the tension and one side will be the compression. So compression will be transferred by the bearing to this plate and tension will be carried by these anchor bolts. Similarly, in this case, there will be since there is no moment, there will be two forces. One is either direct tension or compression, and other will be the shear. So we have to design the bolts as we discussed. For the shear, either we can provide the shear lug or we can directly provide the welded washer so that the bolt will take all the shear, and the if sufficient compression is there, then that shear will be resisted by the friction between the base plate and the concrete pedestal. So we'll start with the design. So I have prepared one example for this base plate design. Okay, so first we will consider the pin connection base plate. Okay, so for pin connection, what we are going to assume, the axial load is of 1000 kilonewton. This is compression load. Tension load, tension in the bolts will be 40 kilonewton. So this will be the single bolt or tension in the single bolt. So first, what we have to decide, the area. What is the area required? So there are two couple of things or two criteria to select the size of the base plate, right? One is based on the total compression or the area required to transfer the total compression to the concrete pedestal, and second based on the section size available or section size used. So first criteria is to transfer the total compression force onto the pedestal, concrete pedestal. So that as we are saying that the total compression will be transferred to the bearing type or bearing of base plate against the pedestal. Since we are considering base plate as sufficiently rigid enough so that it will transfer the equal pressure on the pedestal. So what is the bearing stress for the concrete? For concrete bearing stress is, for limit state method, it is 0.45 FCK. So for our grade of concrete, if we consider 30 Newton per mm square grade, then our bearing stress will be 13.5 Newton per mm square. Okay, yield stress will be 250 and permissible bending stress is 187.5. This is 0.75 times of the 250. This is yield stress, permissible bending stress in the plate element. Okay, so we have this bearing pressure. So to to transfer this 1000 kilonewton of load, we have this bearing pressure. So based on this, we will get the area of plate required. So based on that, we got the area of plate required is 74074 mm square, right? Mm square. So now we just need to work out the bearing. So based on this, we'll just work out the square. We will assume the square size of the base plate. So once we take a square root of this area, we'll get the one length of the base plate. So minimum size of base plate required so that this bearing stress will not exceed due to this 1000 kilonewton of load. So for that we need a 272 mm by 272 mm square base plate, right? So this one size you got it based on the loading. Now the second size will be based on the section size provided. So in this case, we have provided a section of ISMB 300. So for ISMB 300, when we want to weld this plate along with this column, we need to have some space on either side. So for that, we'll consider 25 mm on either side. So one length you will get for the plate will be 350, right? And other in other direction, either you can make it a rectangular plate or you can make it a square plate. So we have considered here square plate. So the base plate size provided will be 350 by 350. Based on the load, we require 272 mm, and based on the section provided, we need 350 square. So now we have to calculate the actual pressure, what is coming below the base plate. So earlier it was 13.5 Newton per mm square or 13.33 Newton per mm square. Now since we have provided the larger base plate, then our actual pressure will get reduced, and that pressure is 8.16 Newton per mm square. How we have arrived at this pressure? We have just divided by this 1000 kilonewton by 350 square, 350 by 350. So we have just worked out the stress or pressure acting from the bottom. It is same as that of foundation design, right? During foundation design, what we assume, we have the load, we assume we consider the bearing capacity, and based on that we work out the preliminary size of the footing required. So it is same as that of footing design. So we have worked out the preliminary size or plan size of the base plate. So the required size will be 350 by 350, based on which our bearing pressure is 8.16 kilonewton, 8.16 Newton per mm square, which is less than 0.45 FCK or 13.5 Newton per mm square. Okay, so this is how we have decided the size of the footing. Now, can anyone tell me why we have provided this bolt in the both direction, 120, 120, or same in both the direction? Why we cannot reduce on one side, or any idea?
सर वो डिजाइन इकोनॉमिकल बनाने के लिए,
No,
ताकि इक्वली डिस्ट्रीब्यूट हो सके वो फोर डायरेक्शंस में.
not really. Actually, even if since it is a direct, it is pin connection, it is direct, so we can provide like this also. We can provide like this also. Anyone? See, when we provide bolt in square, like one in both the direction, same orientation, because what happens, the bolts are casted as we studied. These are the cast in situ bolt, right? So bolt are casted during the casting or bolt are embedded during the casting of pedestal. So no, at that time we don't have a base plate or structural steel, nothing is there, only we provide the embedded anchor bolt. If you provide different spacing in both the direction, right? So if I have provided this kind of arrangement, something like this, so what will happen if by chance or by any mistake, if the site contractor, if he just rotate the bolt like this, by mistake if he place like this, but my uh, base plate, how it will have the holes? The base plate will have hole at this location, right? So these are the holes in the base plate, whereas site has casted anchor bolt at this location. So in that case, this design will be the way, it will not waste, but the hole whatever provided in the base plate, that will waste, and again we have to drill a hole here. But if there is sufficient space, then it is possible. If not, then these two holes will get combined and it will become a slotted hole. So that's why, in order to avoid that, what we do, we provide the bolt orientation or spacing between the bolt in both the directions same. So even if you do any mistake, then also we will be able to fit the base plate to these anchor bolts, right? He can rotate the bolt in any way what he wants, but the ultimate, the spacing between the bolt will remain same. So we don't have to bother about the placing of the anchor bolts in case of square type of arrangement. If you provide a rectangular, then it is very difficult, or there could be a chance of making error on the site, and that will cost during the erection procedure, because all the structural steel and columns will be at site, and during that time, if they notice that if the bolts are not in line, either they have to cut the base plate, put new base plate, or manufacture new base plate with the revised holes, or they have to trim the anchor bolt, then they have to do some hilti. So in order to avoid all those things, it is always recommended to have the square base plate as well as square bolt holes, right? If you don't provide a square base plate, what will happen? If it may, there may be a chance that the base plate orientation will get changed. So that's why it is always recommended to have the square base plate and square anchor bolt locations. Okay. So now let's start. So first we got the pressure. Okay. So now bolt base plate will be designed for the two forces, right? So we got the plan size of the base plate. Now what we want? We want the thickness of the base plate. How much thick base plate shall be there for the given loading? So that will be governed by two factors. One is due to the bearing pressure acting from the bottom of the base plate, and second will be the tension in these anchor bolts, right? So because of bearing pressure from the bottom, what will happen? The base plate will try to bend, right? Just show you if I have detail. Okay, so let's consider there is a pressure from the bottom here. Okay, this is base plate. So what will happen? It is same like a footing. Your footing has same arrangement. If there is a pressure from the bottom, and it will be cantilever for this much of length, right? For this much of length, this plate is cantilever, right? So it will try to bend, right? It will try to bend. Similarly, footing like footing type. So for this cantilever part, we have to work out the thickness of the plate by calculating the movement. So how we will calculate that? So effective width for the bending. So effective width is how much? This is 112. Okay, so first we will calculate the movement due to the base pressure. Okay, so here what we have considered, we have already provided some stiffeners here. So three stiffeners are there. You can check with without stiffener also. If there are no stiffeners, then how the plate will look like. If there are no stiffeners, plate will look like this. And what will be the cantilever portion? So this will be the cantilever portion. This much of length. This 105 will be the cantilever portion. So for this 105, we have to work out the thickness. But actual cantilever will be from this space, right? So conservatively, we can consider this much length of the footing as a cantilever, because at for certain part it will give the resistance for the bending, uplift bending, but later on we have the support at this wave, right? Are you getting the bending of the plate where it will bend when the load is acting from the bottom? So it will try to get support, some support at this flange. After some length, this flange support will not work, and the plate will try to bend against this wave. So this is the actual effective length, or actual length, or length of the cantilever portion. So for this length, we have to calculate the thickness. So this is the one option. Another option is to provide directly the stiffeners. So by providing stiffeners, what we are doing, we are just confining the plate between these stiffeners. So these stiffeners will provide a resistance against the bending due to uplift force. So once these stiffeners are provided, then our plate got stiffened. So how it got stiffened? It got stiffened between these stiffeners and this column. So in this case, if we see, the plate has got support on the three sides. This is one side, right? If I consider plate of this area, okay, I'll just move the hatch. So this is the plate area which is getting stiffened against this steel column, this one stiffener, and this is second stiffener. So actual now the unsupported length remain is only this much. So in this case, we can say that the plate is supported on three edges, right? Similarly, this portion is also getting supported on three edges. So now for us, the purely cantilever plate is only this much, which is only 18 mm, right? 18 or maximum 25 mm. So here, so when we are considering plate supported on three edges, right? So A is 142, that is free edge, which is 142. B is 170, that is the distance of free edge from the web, right? So this is A and B dimensions. So have you heard about the Rokes formula ever? Anyone has heard it? Anyone has
No, sir.
used? Uh, Anyone know the Fourier series for
Yes,
the plate
yes,
stresses
sir.
calculation?
No, sir.
Yes.
If anyone has done MTech, in that there is some subject, I think plates and shells. I don't know it is there or not, but during our time it was there, that plates and shells was one subject where the stresses of the plates is calculated by using the Fourier series. Fourier series we studied in the math. Based on that theory, uh, there are some equations which will provide the stresses for the plates when the plates are fixed at different ages. So you can find these formulas or these stress table in Rokes formula, where you can get ready-made stresses, or how to calculate the stresses for different plates supported at different ages. So in our case, we are considering the plate is supported on three edges, one, two, three. So for that, A and B, A is this free side, B is the distance of free edge from the support. So that we got it. So you have to draw the this connection detail actual so that you can get these distances. Okay, so from this we got A and B. So now we have to calculate A by B ratio because these coefficients are given, these bending coefficients or stretch coefficients are given based on the ratio of A by B, that is unsupported length to the fixed length. So A by B ratio we are getting 0.84, so which is falling in between the 0.75 and 1. So based on this, what we required, beta 1, beta 2, beta 3, right? What is this beta 1, beta 2, beta 3? These are the bending stress in the plate at different locations. At x is equal to 0 and z is equal to 0. So at z is equal to 0 means at this location, and at x is equal to 0 means this location. So this is at the center of the plate. Okay. So center of the plate we have beta 1 at x is equal to 0 and z is equal to b. At x is equal to 0 and z is equal to b. So it is at free edge. This is beta 2, and at x is equal to a by 2 and z is equal to b. So at x is equal to a by 2 here. So this x is equal to 0 is at this location. Huh? Please consider this one. X is equal to 0 at this location. X is equal to a by 2 at this location. So at x is equal to a by 2 at this location and z is equal to b. So it is at this fixed location. Okay. So for these beta 1, beta 2, beta 3. So out of these three, we have to consider the maximum bending stress or the coefficient which will produce the maximum bending stress in the plate. So our ratio falls between 0.75 and 1. So corresponding to this beta 1, beta 2, beta 3, we will consider the, by interpolation, we can consider the these factors. So here on conservative side, I have considered the factor corresponding to 1, that is 0.321, 0.259 and 0.511. So these are the three factors, beta 1, beta 2, beta 3, I got from the ratio of A by B. So maximum bending stress will be beta 4 q into b square into divided by t square, right? So what is maximum beta is? So this should be beta 3, not beta 4. So 0.511 into 8.163. So what is this 8.163? This is the pressure what we got from the size of the base plate and compression load. So this is the pressure, and b square. B square we got it here. So this is the length of the plate which is unsupported. So this is 170 square divided by t square. So this is the bending stress in the plate, and permissible bending stress in the plate is 187.5. This is given in the code how much percent we should consider. So it is around 75% of the yield stress. So that bending stress we know the movement in the plate, so we just need to work out the thickness. So this is actual, this expression is what? Stress is equal to movement divided by the section modulus, right? Bending stress is equal to movement divided by mz. It is m by z. So this is your movement. T square is your stress, section modulus. So corresponding to this movement, the thickness required is 25.4 mm, right? So we got one thickness, right? So from pressure we got the thickness of the plate. This is this movement, this thickness is due to the compression or compression in the section, or at compression at the support location. Now due to the tension, so there will be a tension in the bolts. So what will happen when there will be a tension in the bolts? The plate will get lift, right? It will get lifted up, and what will create? It will create a deflection in the plate, right? So when there will be, so if this is the plate, and if this is the bolt, so if bolt is having tension, what will happen? The plate will try to lift like this, or it will bend like this. So there will be a deflection in the plate, right? So what we have to check here, when there will be a tension in the bolt, we have to check the deflection due to the this point load, right? The plate is fixed on three edges again. So this stiffener will resist the it will support the it will try to control the deflection of the plate, or plate will try to bend between these two surface. So we have to check the deflection in both the direction. One is for this portion, this cantilever beam, and another for the fixed end beam where the load is located at intermediate level. So we just need to compare these two deflections, right? Thickness, how we can control the deflection? By increasing the thickness or depth of the section. For any member, when it fails due to deflection, we normally increase the depth of the section, right? For concrete also, if beam is failing in deflection, we increase the its depth. For slab also, we increase the thickness of the slab so that it will pass in the deflection. So similarly, due to this tension or due to this point load, we have to check the deflection of the plate for two cases. One will be the cantilever portion like this, right? How will be the cantilever portion? If I just draw a section here, if I just consider a section here, how will be the plate? Plate will be like this. It will be fixed on this side for the column, right? It will be fixed to this web, and bolt will be somewhere here, and there will be a tension, right? So due to this tension, what will happen? It will try to bend, and there will be a deflection. So this is a cantilever beam. So if we draw just a free body diagram, so this is my cantilever beam, and it will have the load acting in this direction. So we just need to work out the deflection. So how will be the deflection? So deflection will be deflection will be somewhat like this, right? When it is lifting the plate. So since this is fixed end, this is free end, and because of that tension in the bolt, the deflection will be like this. So this is for the cantilever portion, this much of portion, or for this much of portion, and other case will be for the load acting at intermediate level. So the other case is like this. We have a beam here. It is fixed at both the end, and somewhere load is acting in at this location. So this is A distance, this is B distance, for which we have to calculate the deflection. So for that beam where the load is acting at some level at intermediate distance, then P into A cube B cube divided by 3A into A plus B cube. So you can find this expression in your, I think, second year book also. When the load is acting at a certain distance from the support, for the cantilever portion, what is the deflection equation? So we are just comparing the deflection in the both direction. One is for the cantilever, another is for the fixed beam. Remember, this is a fixed beam, not for the pin beam. For fixed beam supporting having load at the somewhere uh, on the length of the member. So based on that, we got the px and py, ratio of px and py. So it will be 0.22 because we have all the parameter x. X is 56. Means this cantilever distance or the distance of the wave from the bolt center, this x is 56, y is 55. So another distance is this 55, and y2 is 87. So once we draw the geometry, or once we draw the configuration of the base plate, we'll get all these distances. So okay, based on that, we got one equation, pxy py, its ratio is 0.22. But actual tension in the bolt, it is how much? It is 40 kilonewton, right? So Px plus Py, so both these forces should contribute to the 40 kilonewton. So based on this, we will get the, just by solving these two equations, we will get the Px and Py. So what is mean by this Px and Py means how much load is getting transferred to this edge and how much load is getting transferred to these other two edges. So here we can see that Px, we are getting maximum load on this cantilever edge, that is 32.84 kilonewton, and Py it will be 7.16 kilonewton. Okay, so for these loads we just need to work out the again moment. So that moment will be 32.84 into this distance, that will be one moment, and for other load it will be this fixed end moment based on the load location. So for these two moments we have to calculate the thickness required. So for Tx required, one is 13.92 mm, and Ty or the other moment we require 10.7 mm. So this is, we got another thickness. So this is based on the compression, this is based on the tension when the plate is having three supports, or plate is supported or fixed on the three sides. And for the corner panel it is same. We have, actually we don't have any corner panel for this pin type connection. So for pin type connection we got the two thickness. So maximum of these two will be the thickness of base plate required. Okay, so for pin connection we have just worked out the thickness required based on the compression and tension in the anchor bolt. This is clear? Up to this part it is clear?
Yes, sir.
सर इसमें पीएक्स और पीएवाई कौन सा है?
Px and Py we have to find konsa means in which direction it is.
हाँ यस सर.
So Px is for this member where y1 and y2 is there, and Py will be this. So Py into this x, you will get the moment in my direction, right?
तो इसमें एम एक्स एम वाई ये सब हम लोग कैलकुलेट करना है.
हाँ वो करना है ना, तभी तो आपको थिकनेस मिलेगा. यू नीड सम मूवमेंट टू कैलकुलेट द थिकनेस, राइट? थिकनेस मूवमेंट के लिए हम थिकनेस वर्कआउट करते हैं ना. सो यू हैव टू कैलकुलेट द थिकनेस. व्हाट वी आर कैलकुलेटिंग, वी आर जस्ट कंपेयरिंग द डिफ्लेक्शन ऑफ द प्लेट व्हेन इट इज सपोर्टेड ऑन डिफरेंट एजेस, और उसके हिसाब से कितना कौन सा एज या कौन से एज पे ज्यादा फोर्स ट्रांसफर हो रहा है. इट इज लाइक वन वे स्लैब, राइट?
सर
वन वे.
एक बुक का नाम बता दीजिए ना मुझे, नहीं मैं पढ़ लूंगा उससे, क्योंकि दिक्कत
आपने
हो रही है. हाँ,
ये जो टू वे स्लैब का कोएफिशिएंट पता है आपको?
वो मैंने पढ़ रखा है, मेरे पास उसका, लेकिन स्टील में नहीं, ध्यान नहीं है सर उसका.
नहीं नहीं, आप कंसेप्ट समझ लो. बोथ द कंसेप्ट्स आर सेम. टू वे स्लैब का जब आप कोएफिशिएंट्स निकालते हो,
जी सर.
one way continuous, two way continuous, let me show you. The same concept is here. You cannot find these things in the book. These are like practical approach when we work in the field. In book you will find only calculating this pressure, like this movement for cantilever portion,
ओके सर.
and you can just find the thickness required for that. So whatever we have shown here, this Rogue's formula or this deflection part, it is all during the field when you perform actual design in some office or for any consultant. Over there you will find this type of design procedures. In books it is not there. So these are the simplest ways to calculate the thickness of the plate. For these coefficients, you can go for this two-way slab coefficients are there in our IS code. I think I'm not sure. Slab spanning in two directions, right?
यस
So
सर.
here they have this concept. Interior panel one short edge continuous, one long edge discontinuous, two adjacent edges discontinuous, right? Then two long edges discontinuous. So in our case, what is the condition now? So this is the long edge, long one long
One
edge
long is discontinuous.
discontinuous. Okay. So do
Third
we have
one.
one long edge discontinuous? So we are falling in this category, third one, and short span coefficient. Okay, it is based on value of Ly by Lx. So it is based on the Ly by Lx. Similarly, it is for plates we have used A by B ratio, right?
Yes, sir.
So it is the same concept what we are following for this base plate. तो ये रोल्स फॉर्मूला आप यूज करो उसमें there are too many conditions. One is discontinuous, other is fixed pin conditions. Let me check if I have that one. Let me just show you.
कोई नहीं सर, आगे बढ़िए, कोई दिक्कत नहीं, हम देख लेंगे। डिजाइन ऑफ स्टील का बुक है सर मेरे पास, सुब्रमण्यम का, उसमें
उसमें नहीं मिलेगा ये मेथड नहीं मिलेगा उसमें। आप कौन से भी बुक में ढूंढ लो, ये मेथड नहीं मिलेगा आपको।
कुछ
उसका
बेसिक तो मिलेगा सर, उसमें देख लेंगे।
उसमें बेसिक मिलेगा आपको कि कैंटिलीवर है तो मूवमेंट निकालो, स्ट्रेस इज इक्वल टू m by z, m is the load total base pressure into the cantilever portion that will give you the movement, और z के लिए 1/6 into b into t square, और
जैसे
बेंडिंग आपका है सिग्मा बी जो है वो 187.5, उसके हिसाब से थिकनेस निकाला। दैट्स इट, इतना ही मिलेगा आपको बुक में। बट लेकिन जब टेंशन आता है बोल्ट में तो प्लेट का बिहेवियर कैसा है, उसमें क्या होगा, तो देर विल बी अ टेंशन इन द व्हेन देर विल बी अ टेंशन द प्लेट कैसे बेंड होगा, तो वो सब नहीं मिलेगा। और ये जो कंसेप्ट है रोक्स फॉर्मूला से निकालने का, दिस इज द
यस सर,
इजीएस्ट वे,
ओके सर।
राइट।
सर पीपीटी आप मुझे सेंड कर देना ग्रुप में सर।
हाँ, ये एक्सेल में डाल दूंगा, ये इसमें बहुत सारा कनेक्शंस भी है। एक बार हमारा कनेक्शन हो जाता है तो मैं एक्सेल डाल दूंगा।
सर वो डिजाइन पैरामीटर भी
हाँ, वो भी दे देता हूँ मैं
ये
आपको।
वाली सर भेजी हुई है सर, ये शायद एक्सेल
भेजिए।
शीट है ना, ये है। हाँ अविनाश भाई,
हाँ
ये वो सर ने जो स्टील का वो मटेरियल भेजा था ना, उसी में एक्सेल शीट है, एक बार चेक करना है ये वाली।
अच्छा, मैं मेल पर देख लूंगा, ओके।
हाँ
ये जो आपको चाहिए ना, मैं आपको व्हाट्सएप पे डाल देता हूँ, तो आप ग्रुप में डाल दीजिए, क्योंकि आई थिंक मैं जो आपका ग्रुप चल रहा है अभी उसमें ऐड नहीं हूँ मैं, तो मैं
ओके सर।
उसमें नहीं डाल सकता। तो मैं तो आपके व्हाट्सएप पे शेयर कर देता हूँ। शायद आपने ही मैसेज भेजा था ना आज मुझे।
नहीं सर, मैंने कॉल किया था आपको।
आपने कॉल किया था, तो किसका
अब मैं
मैसेज?
मैसेज कर दे रहा हूँ अभी।
हाँ, ये 767 एंड में किसका नंबर है? आपका आपका नहीं है क्या?
नहीं सर, 9911 होगा मैं लास्ट में, भेज रहा
अच्छा,
हूँ सर।
का तो था फिर ये।
भेजा हूँ सर, मैंने हाई करके भेज दिया।
हाँ है।
हाँ
मैं
वही है मेरा।
आपको पे ये पैरामीटर और विंड का कैलकुलेशन ये सब डाल देता हूँ,
यस
तो
सर।
आप आपके ग्रुप में भी फॉरवर्ड कर दीजिए उसको।
ओके सर।
तो अभी फिक्स्ड एंड कनेक्ट, फिक्स बेस प्लेट कनेक्शन।
Sir, sir,
हाँ,
one
बोलिए।
minute. Sir, 120, this distance, how you got it between the bolts?
This 6 times diameter of the bolt. In anchor bolt we discussed, right? Anchor
Okay,
bolt,
sir.
6 times of bolt diameter, that should be the distance between the minimum spacing between the anchor bolts. Just show you. cast in anchor bolts minimum 6D. So 20 mm dia bolt, so we considered the 120 mm. So that's why we got this 120, 120 on both the sides. Okay.
Okay, sir.
So so now fixed type of connection or fixed base connection. So what is the difference here in fixed type fixed type connection? You have
Sir,
all
please share the screen.
screen is not visible.
सर एक
Oh,
मिनट सर वो
just
बीम कॉलम में हम लोग जो एल एक्स एल वाई एल जेड दोनों चीज में अलग अलग एल एक्स एल वाई एल जेड लगे हैं सर ना
हाँ
एक पूछना था बस ठीक है सर
एक मिनट है मेरा नेट का थोड़ा इशू हो गया है लैपटॉप के लिए होल्ड कीजिए to restart the laptop. Okay. So now fixed type of base plate. So now in fixed type of base plate, this portion, is it same as pin type connection? Only this portion we have to check for the bearing pressure from the bottom. There is no anchor bolt, so we don't need to check for the tension in the anchor bolt for this much of portion. So this portion is same as that of pin type connection, only having base pressure acting from the bottom. So this, yes,
No, sir.
okay. This portion, it is plate supported on three sides. So again, we have to follow this method, calculating px, py, and comparing the values and calculating the two thickness for the two movement. One is for this movement, another will be for the fixed beam supported, fixed beam having a point load at some intermediate distance, right? The only difference in case of fixed type is this corner, right? We have to work out the thickness for this corner portion. One is for the base pressure, it will be supported on two edges. Again, so again we will look for the plate supported on two edges, and we will work out the thickness for this portion. And for the tension in the bolt, it is quite simple as compared to this one. Here also, here we need to work out the two, we have to consider the two different equations for the deflection, but in this case we have to consider one, because it is cantilever from this side as well as cantilever from this side. So both the equations we have to compare, px cube and py cube, right? X and y, it is cantilever from both the sides. So these two, after comparing these two, again we will get the px and py ratio, and we know the px plus py are total tension in the bolt. So again, comparing these two equations or solving these two equations, we'll get the force, contribution of force by that edge, and again getting the moment from these two forces, cantilever moment we will get for px and py, and we'll get the thickness. So for this, out of this, for the fixed base, how many thickness we will get? One is for the base pressure for this plate supported on three areas. Second thickness will be for this plate supported on three sides when there is a tension in the bolt. Fourth thickness will be for this corner portion or cantilever portion due to the bearing pressure, and fourth thickness will be due to the tension in the anchor bolt when this plate is fixed on two edges or two edges discontinuous. So out of this four thickness, whatever is maximum or whichever is maximum, that will be the thickness of base plate, right? Understood this? Only difference is this corner. Clear this thing for fixed base plate connection?
Yes, sir.
So it is quite simple to calculate the base plate thickness. If you don't need to pass on the shear to the anchor bolt, you just provide a shear lug at the bottom that will take care of all the shear on anchor bolt. You just need to design the anchor bolt for the tension, and base plate you have to design it for the base pressure and tension in the bolt. So that will give you the thickness for the tension as well as for the compression. Okay, so any doubt in the base plate design? Any doubt?
No, sir.
हाँ, आपका
सर
क्या
ये
था? एल वाई, हाँ हाँ बोलो।
बोल्ट डायमेंशन ये कौन सा साइज रहेगा बोल्ट का, ये डिसाइड कैसे हुआ सर?
ये हम स्टार्ट में तो मिनिमम M20 प्रोवाइड ही करते हैं। बोल्ट का डायमीटर जो है मिनिमम 20 mm हम प्रोवाइड ही करते हैं। So based on that, you can select 20 diameter and 6D is the distance. Agar that number of bolts, or the, 4 bolts normally we provide for the base plate. If that is not sufficient, then go for the higher size of the bolt. So it's like some trial and error, or you can just check based on the support reactions. You will get the tension in the bolt. Okay, you will get the tension reaction, right? You can just compare that capacity of one bolt, how much is the capacity. So based on that, you can just work out, if I select 20 bolt, how much will be the capacity, or how much will be the utility ratio of those 4 bolts. If not, then you can go for the 24 dia bolt. If not, then 30. So, and as you go on increasing the diameter, you have to increase the distance, or a center to center distance between the bolts.
Okay, sir.
Sir, how you will give fixed butt joints, sir? Fixed butt type support.
Fixed butt type is the same one. So this is fixed type, but it is released in this direction. This is fixed butt type. If you want to have fix in both the direction, then there will be some bolts here as well and here as well. If it is fixed in both the directions, so there will be some bolts somewhere here and somewhere here. Right? So this will be a fixed from all the sides. But in this case, it is a uniaxial bending, only bending in this direction, and in this direction it will be a pin type connection. Got it?
Sir, in our example, we have given one support for the middle column, fixed
Mhm.
butt type. No?
So it will be this type of connection. In this direction we have bracing, right? I'll just open the stand. So when we provide fixed berth, it's not this stand. Yeah, we have provided pin type connection for all the support, right? Not fixed berth. We have not put any fixed connection, because in this direction we have braced, and in this direction it is connected at the top, where there will be a movement connection for the beam. So in this direction it is also pin. When we provide fixed berth, it means that in one direction we are having movement, and in other direction it is fixed. So when we have a connection, if you want to make a fixed type of connection for the center column, it will be same as it is orientation, and for the other columns it will be simply like this, because column orientation will be like this, right? So if you want to make a fixed butt connection for these columns, then it will look like this. It will be flange will be on this side and bolts will be on outer face, and for the central column it will be like this. So we have discussed about orientation of the column, right, at the beginning of the this warehouse. So it depends on the how you orient the column. So normally 99% when we provide fixed butt, it is only along the flange. Normally we don't provide or put a fixed type connection along the way.
Okay, sir. Sir, from start, how you take the reactions? Can you show that also?
Instead, so once you analyze this, okay, so here we have to select the load cases. post processing, and on this one tab. Yeah, this one. So first select the combinations for which you want to have a reaction. So I just selected the factor combination and range and post processing. Here you can go to reactions. From summary, you will get these reactions. All comparing all the supports. So from this you can see the maximum compression is only 78 kilonewton, maximum tension is 18 kilonewton, and maximum shear is 29 kilonewton. So when the maximum shear is 29 kilonewton, you have axial force of 78 kilonewton. So that shear, actually the friction between the pedestal and concrete, pedestal and base plate, concrete pedestal and base plate is 0.4. So if you select compression of 78 into 0.4 will be the friction coefficient. So actual force getting generated is 31 kilonewton, which is more than this actual shear force. So when there will be a this load, when there will be a this load combination or load reaction due to this wind load, during that time bolt will not have any shear on it, because the compression is such that whatever shear is there, it will be nullified by the friction between the base plate and the pedestal. Now for this case, this is purely tension, right? When there will be tension, then bolt will have this tension, direct tension, as well as this shear. So these two forces has to be registered by the bolts, right? And if you don't want to pass on this force to the bolt, you can just simply provide the shear length. You can just take the maximum one case for the maximum shear and corresponding axial loads, maximum compression force corresponding axial force, and maximum tension or this minimum Fy value, that will give you the maximum tension in the at support location and corresponding shear forces. So these three combinations we will require to design the base plate. Clear?
Sir, not clear.
What is confusion?
How you will use this value for design of base plate? I didn't get that.
What I didn't get you.
Sir, I didn't get your explanation.
See, once we do the analysis, right? So here you, I'll just show you again. This is post processing mode, right? From this tab, result setup, you have to select the load combinations for which you want to design the base plate, right? So once you select all these combinations, then you can go to the reactions. So once you go to the reaction, it will give you the reactions for each and every node and for all the combinations what we have selected, right? So you will get all the forces here. So instead of checking for each and every case and for each and every node, what we will do normally, we go to the summary. Once we click on the summary, we will get some 10 to 12 combinations where in which you will get the maximum shear, maximum compression, and maximum tension. So first thing is, one we got the case. So this is the 104 case. So we have to select the three combinations. One is for the maximum shear, one is for the maximum compression, and third one is for the maximum tension, right? So first case is for maximum shear. So which is this one? So 104 load case, and it is at node 6, right? So I got the maximum shear and corresponding axial force I will consider for the design. Then second case, what I have to find? I have to find the maximum compression. Now maximum compression is this case. This is again 104 case. So I am getting maximum compression of 78 kilonewton, and I have to consider corresponding its shear value for the design of anchor bolts. Then third one will be the maximum tension, where I am getting maximum tension for load combination of 103. Maximum tension means minimum value in the FY column, right? Vertical minimum value is your tension. So I'm getting tension of 18 kilonewton, and corresponding shear I have to consider to design the anchor bolts, right? So I got the three combinations. Now when we are considering maximum compression, compression is 78 kilonewton. So what it actually doing, it is pushing the base plate against the pedestal, but at the same time there is a the shear force. So it will try to slide the base plate, but due to the compression there will be a friction between the concrete top and base plate bottom. So that friction is 40% of this compression load or vertical load. So that is coming 31.2 kilonewton, which is more than the actual shear coming. So the friction between the pedestal and concrete is nullifying the actual shear coming due to the design forces or due to the combination. So that's why we don't need to design anchor bolt for any shear in this case, particularly for this case, right? We have to design the base plate only for the base pressure acting from the bottom, right? There is no tension in the anchor bolt, so we don't need to check for the tension or pull out uh, deflection of the base plate when there will be a tension in the anchor bolt. Since there is no tension in the anchor bolt, all bolts are free from tension and shear. Only we need to design the base plate. Clear, or still confusion is there?
Yeah, now understanding, sir. Yes, getting.
Okay. Any more queries?
Sir, in practical case, when we give the purlins above the rafters,
Hmm?
so yeah, we need to consider the LY or LX values as the purlin
No, no,
spacing.
no, no. You cannot consider the purlins restraint for the rafter design, because if you see the, I'll just show you the sketch. Because those are not directly connected to the rafter. We cannot consider its advantage or its LY and LZ. See, here you can see this is Z purlin, right? This is Z purlin. It is connected with this clit angle, right? It is connected with a clit angle, with small clit angle. So we should not consider its advantage for the rafter design. We should not.
Okay, sir. Sir, if we have a mezzanine floor,
Mhm.
then is there any criteria for choosing the direction of primary and secondary beams?
No, actually, when you have mezzanine floor, I'll just show you the diagram. I'm just preparing one mezzanine floor plan, not the mezzanine, but like a deck slab. So in this case, there is no need to consider any direction or a section, primary or secondary, but it depends on the your metal deck sheet. The metal deck sheet will have some spanning. This is prepared by the manufacturer. and it has some spanning limitations. So it may span up to 1.5, 1.6 meter. So accordingly, you have to place the beam at at that spacing, and then you can decide, or then you can put a concrete slab over it. I have not developed section for it, so it's something like this. So there will be some beams at the bottom and concrete at the top, and there will be a sheeting here on steel beam, which will be covered by this concrete. So spacing or spanning depends on the sheet span.
Okay, sir.
Any more queries?
No, sir.
Okay, if no more queries, then we'll stop here, and maybe tomorrow or day after tomorrow we'll start with the connection design. So initially we'll go through some theory, then we will go through all these examples, and then last session will be on the gantry girder. So let's try to finish before 14th. We'll try to finish everything before 14th or 13th. If any queries, then we'll keep one another session just to resolve the queries. What if you have? Okay. So
Okay.
we close the session. Okay. Good night, everyone.
गुड नाइट सर। सर वो डिजाइन पैरामीटर सेंड
Good
कर
night,
दीजिए।
sir. Thank
हाँ
you.
मैं भेज देता हूँ, भेज देता हूँ।
ओके।
Okay.
Good night, sir.